Hi everyone, welcome back to Studying with Zahra. Today we're going to be doing biological molecules, specifically an introduction to biological molecules, as well as carbohydrates. So let's get right into it. I'm going to be doing AQA biology, AS level, and I'm currently just using the textbook. So basically, atoms combine with each other in a number of ways, and we've learned about this in chemistry as well. So essentially there's three main types of bonding. There's covalent bonding, ionic bonding, and hydrogen bonding. Now covalent bonding essentially consists of the sharing of electrons in pairs, and then ionic bonding consists of the loss and gain of electrons between atoms of an element, and as a result your atoms turn into ions, which are essentially charged particles, and these particles are oppositely charged, and so they'll attract each other in a process known as ionic bonding. Now, they've given an example here of the sodium ion being Na+, and the chloride ion being Cl-. As a result of the fact that they have opposite charges, they will attract to each other. Now, one thing that's really important to bear in mind with ionic bonding is the greater the charge on the ion, the stronger the ionic bond. So, for example, if I have an ion with a 2+ charge, so you know how Na is just 1+? If I have an atom with a 2+ charge, which I think magnesium would be Mg2+ in its ionic form, I'm not 100% sure. I don't have my periodic table on me. And if that binds with another ion that has a 2- charge, the ionic bond that forms between these two ions is far stronger than the ionic bond that forms between a 1+ and 1+. Now, hydrogen bonding is quite interesting, and it's something that's a little bit new. So I'm going to go over it in a bit more depth. Now, the electrons within a molecule are not evenly distributed, but tend to spend more time at one position. This region is more negatively charged than the rest of the molecule because essentially the electrons are spending more time there. And we know that electrons are negative. A molecule with an uneven distribution of charge is said to be polarized, or in other words, is a polar molecule. The negative region of one polarized molecule and the positive region of another attract each other. So it's kind of like ionic bonding in the sense that we have a negative and positive attracting, but it's for the same molecule. A weak electrostatic bond is formed between the two, and although each bond is individually weak, they collectively form important forces that alter the properties of molecules. This is especially true for water, and you may have heard that water is polar, and we'll learn more about that in a second. So once again, an uneven distribution of electrons, you can see my notes on the right. It occurs when electrons spend more time at one region of the molecule, and so you have that region of the molecule being attracted to the oppositely charged, slightly positive region of the molecule, resulting in a weak electrostatic bond that collectively forms a strong, important force. Next, we're going to be learning about polymerization and the formation of macromolecules. And don't be thrown off by any of the complicated names. We'll come across a lot of complicated names in the time that we're doing AS and A2 biology, but I think it's all about just trusting the process and breaking everything down. Certain molecules known as monomers can be linked together to form long chains, and these long chains of monomer subunits are called polymers. So essentially, a monomer is a very simple, basic unit, and we have all of our monomers joining together with other monomers, forming a chain, which is known as essentially a polymer. Poly means many, and I think mono means one. Now, the monomers of a polymer are usually based on carbon. Many, such as polythene and polyesters, are industrially produced, and we learned about these in chemistry. Others, like polysaccharides, polypeptides, polynucleotides, are made naturally by living organisms. We learned about polypeptides in proteins and how amino acids join with one another to form a polypeptide chain. And so you might start seeing the pattern, but amino acids are essentially the monomer in this case. And the fact that they're bonding to each other and forming a chain suggests that the polypeptide chain is actually the polymer. Now, others, like polysaccharides, polypeptides, are made naturally. The basic subunit of a polysaccharide is a monosaccharide or a single sugar. For example, glucose. Polynucleotides are formed by mononucleotides. So you're kind of seeing the pattern. Polysaccharide is made by a monosaccharide. We have the same saccharide kind of ending, and then the prefix is different. Polynucleotides are formed by mononucleotides. Polypeptides are formed by linking together peptides that have amino acids as their basic subunit. Next, we have condensation and hydrolysis reactions, and this is actually pretty fun to learn about. So, in the formation of polymers via polymerization, each time a new subunit is attached, a molecule of water is formed. Now let's just break this down quickly. Essentially, when you have your monomers and they bind to one another, or they form bonds with each other in order to form a polymer, every single time a bond is formed between two monomers, one molecule of water is produced. Or is formed, essentially. Reactions that produce water are called condensation reactions. And you can kind of remember that because we learn about condensation in terms of when a gas cools down, it turns into water, or it turns into a liquid, and you may see, in your bathroom mirror after you take a shower, the steam actually turns into little droplets of water if you have a cold mirror. And so you can kind of remember the whole condensing process and the fact that water is being produced. So therefore, the formation of a polypeptide from amino acids and a polysaccharide starch from monosaccharide glucose are both condensation reactions. Now, you might be wondering what's the difference between these two. Amino acids to polypeptides is actually in the protein group, and monosaccharides to polysaccharides is in the carbohydrate group. So nucleotides are a type of monomer, not monosaccharide. And once again, a condensation reaction between two monosaccharides, specifically two monosaccharides, forms a glycosidic bond. Now, if we're talking about something different, like two amino acids, which is also a monomer, in the same way that monosaccharide is a monomer, you're going to have a different bond, and we'll learn more about that in a second. But essentially, once again, a condensation reaction between two monosaccharides results in the formation of a glycosidic bond, and you can kind of remember glycosidic because of glycogen, which is a type of storage molecule for carbohydrates. Condensation enables polymerization, while hydrolysis enables depolymerization. So hydrolysis, as you may have guessed by now, is the opposite of condensation. In condensation, a water molecule is formed, and you have two monosaccharides being bonded together to form a disaccharide and then a polysaccharide. Whereas in hydrolysis, you have two monomers that are already joined. So you might have a polysaccharide or a disaccharide, and the bond between these, the glycosidic bond between these monosaccharides is broken down in order to gain a water molecule, and essentially it's just a process called hydrolysis. So yeah, water molecules are used when breaking the bonds that link the subunits of a polymer, thereby splitting the molecule into its constituent parts. This type of reaction is called hydrolysis, and hydrolysis essentially means water, lysis means splitting, and we learned about that in electrolysis, so that's a little chemistry flashback. Thus, polypeptides can be hydrolyzed into amino acids, and starch can be hydrolyzed into glucose. Polynucleotides can be hydrolyzed into mononucleotides, I'm pretty sure it was called. I don't know. Yeah, mononucleotides. And so here we just have a couple of examples. So polynucleotides to just nucleotides, I suppose, in a process known as hydrolysis. Polysaccharides to monosaccharides in hydrolysis, lipids to fatty acids, and glycerol. So you're going to have, I think, 3 fatty acids in 1 glycerol. Also in hydrolysis. Polypeptides to amino acids in hydrolysis. And all of these occur via the addition of a water molecule. Contrastingly, you have your nucleotides, your polynucleotides, in condensation, resulting in the loss of a water molecule, and that just basically occurs for the rest of the monosaccharides, of the monomers. Now, metabolism is all of the chemical processes that take place collectively in living organisms. So you might hear about the term metabolic rate, perhaps, and that essentially just means the rate at which the chemical reactions are taking place. Or you might be hearing the fact that, someone has a fast metabolism, and essentially that just means that the chemical reactions in their body are taking place at a fast rate. So this could mean that in our day-to-day usage, that could mean that maybe they use glucose fastly in respiration, in turn meaning that they supposedly burn calories faster. Next, we have the mole and a molar solution. Now, the mole is an SI unit, which is just the standard unit that's used pretty much internationally for measuring the amount of a substance, and it is abbreviated to mole, which I genuinely don't get because they just removed 1 letter, but anyway. So 1 mole contains the same number of particles as there are in 12 grams of carbon-12 atoms. 12 grams of carbon-12 atoms contain 6.022 into 10 to the 23, which is essentially Avogadro's constant. And yeah, 6.02 into 10 to the 23. That's going to take a while to remember. Now, a molar solution is a solution that contains 1 mole of a substance dissolved in each liter of solution. Hence the name, I suppose. A mole is the molecular mass expressed as grams. As an example, to make a molar solution of sodium chloride, which is NaCl, we must first find its molecular mass. Now, the chemical formula for sodium chloride is NaCl, which means that a molecule of sodium chloride contains 1 sodium and 1 chlorine atom. The atomic weight of sodium is 23, while of chlorine is 35.5, and you might be wondering, where do I find this periodic table? It is going to be the mass number. The molecular mass of NaCl is 58.5, so a molar solution of NaCl is going to have 58.5 grams of NaCl dissolved in a liter of solution. And I have a little bit of explanation here, but molar solution is essentially 1 mole of whatever substance it is that we're working with in the solution. The Avogadro's constant is 6.022 into 10 to the 23. MR is the same as molecular mass. So for example, 1 mole of Al is 27 grams because 27 is written on your periodic table as your mass number. And so the molar solution is going to be 27 grams per liter of water. Now this is your extension work, and a lot of the times the book might say that it's extra or you might not need to know it, but it's better to know it. I genuinely feel like all the A-star questions, and the kind of thinking outside of the box questions are going to be a lot easier if you go through the extra material in the book. So we have atoms, isotopes, and the formation of ions. Atoms are the smallest units of a chemical element that can exist independently. An atom comprises a nucleus that contains particles called protons and neutrons. The hydrogen atom is the only exception, as it has no neutrons. Tiny particles called electrons, and electrons are significantly smaller in comparison to protons and neutrons, orbit the nucleus of the atom. And essentially this is just chemistry, so I might not go over this. But feel free to if you feel the need to, of course. So yeah. I'm gonna do the questions. 1 proton and 1 electron. I'm pretty sure that's helium. If an atomic particle, oh, is it? Is it helium? Maybe it's hydrogen. Yeah, it's hydrogen. My bad. If an atomic particle with no charge is added to this element, state what general term can be used to describe the new form of element. It's going to be an isotope because we're adding a neutron, because a neutron is an atomic particle with no overall charge. Determine by what percentage the element's mass number is altered by the addition of this new particle. So we used to have a mass number of 1, and now we're going to have a mass number of 2. So it's going to be altered by, I suppose, 100%. Determine how the atomic number is affected by the addition. It's going to remain the same because we're adding a neutron, and the atomic number is the number of protons, and the number of neutrons has no effect on the number of protons. State what is formed if a negatively charged particle is removed. It's going to form a ion because it's going to be charged, specifically a positive ion because we're removing an electron, and so there's going to be an imbalance in terms of more protons. State how the mass number is changed by the removal. The mass number is going to remain the same because we know that electrons do not affect the mass number, instead protons and neutrons do. Next we have carbohydrates, specifically monosaccharides. Okay, so carbohydrates are carbon molecules combined with water. And some carbohydrates molecules are small while others are large. And we're going to go into the nitty-gritty of everything in a minute. So now, life based on carbon. This is pretty much a brief introduction. But essentially, carbon atoms are just really, really friendly, I suppose you could say, and they love to form bonds with other carbon atoms, allowing a sequence of carbon atoms to form various lengths. Hence, you have smaller carbon molecules and larger ones. These form a backbone along which other atoms can be attached. This permits a large number of different types and sizes of molecules, all based on carbon. The variety of life that exists on Earth is a consequence of living organisms being based on the versatile carbon atom. Carbon-containing molecules are known as organic molecules. In living organisms, there are relatively few other atoms that attach to carbon in general. And so life is based on a small number of chemical elements. And you may have thought about this when you were learning about the fact that carbohydrates are made up of carbon, hydrogen, and oxygen. Lipids are also made up of carbon, hydrogen, and oxygen. Proteins are made up of carbon, hydrogen, oxygen, and I think it was nitrogen and a little bit of sulfur. And so essentially you may notice a pattern of carbon being in all of them. And the reason behind this is carbon just loves to form bonds with each other. And and the reason why carbon-containing molecules are known as organic molecules, and we learn about organic chemistry, And you'll notice how a lot of or pretty much all of the molecules that we learn about in organic chemistry contain carbon in them, hence the name organic chemistry. Next, we're going to be going on to, let me just look at the hint on the side. So in biology, we have certain prefixes. This is going to be super useful. Mono means 1, di means 2, tri means 3, tetra means 4, penta means 5, so like pentagon, hexa means 6, poly just means many, and I think usually it's more than 10. So many organic molecules, including carbohydrates, are made of a chain of individual molecules, and each individual molecule is given the general name monomer. Examples of monomers include monosaccharides, amino acids, and nucleotides. And while we're on that note, the polymers of these monomers are going to be polysaccharides, polypeptides, and polynucleotides respectively. Monomers can join together to form long chains called polymers. We've pretty much gone over this. Most are made up of carbon, hydrogen, oxygen, and nitrogen. Nitrogen is found in proteins, in lipids, and carbohydrates. You only have carbon, hydrogen, and oxygen. And you can just remember the word CHO, so CHO. And then CHON would be for protein, I suppose. In carbohydrates, the basic monomer unit is a sugar, otherwise known as a saccharide. A single monomer is therefore called a monosaccharide. A pair of them is a disaccharide because we know di is 2. Many are joined in via a process known as condensation, in which one water molecule is lost in order to form polysaccharides. Next, we're going to be going on to the examples of monosaccharides. So we have glucose, we have fructose. I believe we have galactose. I'm not 100% sure. Yeah, we do have galactose too. So we have glucose, galactose, and fructose. And then monosaccharides are generally sweet tasting, soluble substances that have the general formula CH2O whole into N, where N can be any number from 3 to 7. Anyways, I think that's going to be all for today. I think I'll go into everything else a little bit later. But thank you guys so much for watching, and please let me know what you guys want to see next.